Well, that takes care of the magic smoke for this series. Hopefully what I build in this series will stop any more magic smoke release, at least from any electrolytic capacitors I might use. In this series, I'm going to be building an ESR meter. ESR, of course, stands for Equivalent Series Resistance. But before I get to the build, let's take a quickie ESR for Dummies course. So to start, here is your typical electrolytic capacitor. Now, the one thing that's common to all capacitors is that they are reactive components. This means that given the same value, construction, and environmental conditions, it will react differently to each signal that is applied to it. Now, for example, if we have an ideal capacitor and we look at the reactance, or for lack of a better word, resistance, at DC, we see that it's equal to infinity ohm. At 60 Hz, 13.263 ohms, and at 6 MHz, 0.000132 ohms. Now, these values are all fine for the imaginary ideal capacitor. Unfortunately, we have to work with real-world capacitors, which will also have some inductance and some reactance that come from the physical properties of the capacitor itself. Now, where do these extra properties come from? Of course, capacitance, the dominant one, comes from the action between the anode and the cathode and the electrolytic dielectric between them. The way this capacitor was built with coils of electrolytic material gives us the inductance. Now, the dielectric used in the capacitor will give us some parallel resistance. Finally, metallic parts like the leads will give us some series resistance. Now, we can model these spare, or to use a better word, parasitic properties with a simple equivalent circuit. So let's start with a capacitor and then add an inductor, then a resistor in parallel, and then a resistor in series. Now we can simplify the circuit by taking out the parallel resistance and just adding whatever that value is to the series resistor. And that is where we get the ESR. Now the boffins who really study this stuff use a lot of complex math, and they're able to come up with all sorts of neat little graphs to illustrate the reactive properties of capacitor. First, we need a graph of ohms versus frequency. And if we graph capacitive reactance, you'll see you get a line that decreases as frequency increases. Next, if we plot the inductive reactance, you'll see you get a line that increases as the frequency increases. The next line is impedance, or the total opposition to an AC current. And you will see that we get a V-shaped line that follows the capacitive and inductive reactance. Now, if we plot ESR, one sees that it's very large at low frequencies, decreases very quickly as frequency increases, and continues to decrease at a very much lower rate as frequency increases. And just for giggles, I added in the self-resonant frequency. And that's the point when the capacitor starts acting more like an inductor than a capacitor. This is normally in the kilohertz range for most electrolytic capacitors, and of course much higher as the value of the capacitor goes down. We care most about this area in the frequency range, which is where most electrolytic capacitors are used, and it's also where ESR is the highest. To put it quite simply, the more ohms you have, the more resistance you're going to have. And the more resistance you're going to have, the more heat you're going to have. If we look at this herringbone graph of the causes and degradation mechanisms of electrolytic capacitors, you can find temperature in almost every single branch. And this, of course, leads to increased ESR and decrease in capacitance and eventual failure of the capacitor because the dielectric is being boiled off from all the excess heat. So, to sum up, high ESR and low capacitance equals a bad capacitor. Well, at least at 60 Hz. As always in engineering, there's a but. ESR and heat are only part of the puzzle, as dielectric makeup, usage and abuse, applied frequency can all lead to differing failure modes. At least with high ESR, we can screen for one failure mode. So that takes care of our ESR for Dummies course. Now before we get down to actually building the ESR meter, let's take a little time and do a practical application of what we learned so far. So let's take these nice graphs the boffins have made for us and put them to some practical use. First, let's just look at the ESR for our imaginary ideal capacitor. Now this plot is not a directly measured value. It is a derived value using this block of vector math that calculates the sum of the real component, ESR, and the complex reactive components of reactance and impedance. Even though this plot of ESR comes from a derived value, we can still use it when designing an ESR meter. As you can clearly see that when the frequency is low, the ESR is high, and its change rate is also nonlinear. So if we try to take an ESR reading At this end of the curve, it will be subject to large swings in value with very minor changes in frequency. So not the best spot if you want to take consistent measurements, as getting exactly the same frequency every time will be difficult. Now if we look at this portion of the ESR plot, ESR is both low and its change rate is almost linear. So in general, this is a better place to do any measurements. Now if we throw up the capacitive reactance plot, one can see that there's a nice sweet spot for ESR, this point here, where the two plots intersect. Both ESR and reactance are the same here. So you need only measure the reactance to get the ESR. We have seen this one before, and it's the resonant frequency. Now the only problem with trying to take a reading at this sweet spot is that you have to know this exact frequency beforehand. Now given that each value, brand, size, batch, and even individual cap will have a different resonant frequency, you kind of get an idea what the dilemma is here. Though it is possible to do this, figure out the exact resonant frequency for a capacitor, and then the impedance at that frequency, it's just not something you can practically put together from spare bits you have lying around the lab. So I think we can give resonant frequency a miss. So that leaves us with this area of the ESR plot, where we know ESR will be mostly constant and reactance will be low. Now I just picked an arbitrary frequency here of say 100 kilohertz. You can see that the reactance here is only 0.008 of an ohm, while the ESR is going to be a little higher at 0.01 ohm. A small absolute difference of 0.002 of an ohm, and a percentage difference of about 25. Okay, that's all fine and dandy for our ideal cap, but what about a real-world cap at the same value, but a very high ESR? Notice how the reactance plot did not move, as this is based on the absolute capacitance value, which does not change in this case. The ESR plot for this bad cap is way up on the graph, with a value of 3.67 ohms. Not that sizable absolute of a difference, but a staggering percent difference of 460. Maybe we can use this difference later on when we design our meter. So what can we conclude from this quickie examination? Well, first off, we need to use a frequency that's in the high kilohertz range, as that will work on the widest variety of electrolytic cap values and with the least measure of error when the testing frequency changes slightly. Also, we know that the values we're going to try to measure are going to be very small, microohms to just a few ohms. So right off the bat, we know we need an oscillator to generate a frequency, some sort of detector, and then some sort of indicator that works at a very small scale. And there's our basic block diagram for our ESR meter. Now we all know the main use for large value electrolytic capacitors is to smooth out AC into DC. Normally a sine wave of 60 Hz, and normally you will get some ripple because of the low frequency involved. Now if you take a square wave and use a high frequency and a low voltage, you will get a distinct step rather than a ripple between pulses. Now given this fact, we can take any old oscilloscope, a signal generator that can create a square wave, and with a known impedance of say 50 ohms, a capacitor to test, and a little math, we can figure out the ESR of a capacitor. First we start with that special square wave, say a frequency of 100 kilohertz and a peak-to-peak voltage of 1 volt and a DC offset of 0, so we don't reverse bias our electrolytic capacitor. Now we can add in the 50 ohms impedance from our signal generator to the circuit and then add in the capacitor that we want to test. We know that there's going to be some ESR involved in that capacitor as well. So if we take capacitance out of the picture, we get a simple voltage divider problem, which we can solve by using this formula, where Vg is the function generator voltage, R1 our known impedance of the function generator, which is 50 ohms. So all we have to do now is take the voltage drop across R, plug that value into the formula, along with V1G and the 50 ohms from the signal generator, and we've solved for R. So let's go down to the bench now and try that on a real oscilloscope. Okay, we're down at the bench now, and I've got my oscilloscope all set up. Fortunately, my new oscilloscope has a nice arbitrary wave generator built in. And as you see, I've got it set for a square wave, 100 kilohertz, 1 voltage point-to-point, 0 DC offset. All I have over here, I'll bend down a little bit, you can see, is just a little T-junction, hooked it into there, and then a pair of grippers right there. So we'll go back up into here, and we'll hook up
this nice low ESR Chicon. And put that in like that. Like that. And as you can see, we get basically a flat line. And if I zoom in, we can measure the ESR by putting up a cursor. On. There's our cursor. And but the delta is about 3 millivolts, so minimal ESR in that one. And now if we take a cheapy cap of about the same value, different shape. This is a radial. That was a radial. Axial. This is a radial. So there's going to be some difference in ESR just because of that. Put that on like that, and you notice in this one we do get a difference. Of course, it's exaggerated because it's at such a small scale. But still, this one has an ESR of about 11 millivolts, 10 millivolts, let's say. So there is a difference. And of course, if I take an old beater like this one, new old stock one, again different one, much lower value actually, 8 millifarad, 8 farad, 8 UF, put that on there, goes right off the scale. There it is there. And the delta on that one, get this right, is way down here. Almost 100 millivolts. So you can see that's how quickly you can measure the ESR with this technique.
So I ran that test in a large variety of electrolytic caps. New old stock ones, new stock ones, pulled ones, big ones, and small ones. So this brief summary table gives you some of the results. As you can see, the really good ones were in the 0.1 to 0.15 range. The average quality ones ranged up to about 0.5 of an ohm. The worst cap I found at almost 100 ohms was a pull from an old All-American 5 radio, while the other was a pull from a switch mode power supply that was failing. So the result of all this testing is that I now know my ESR meter should have a range of about 3 to 5 ohms, as any cap with an ESR over 3 is really just fit for the bin. So now I can go back to my block diagram and add in that 0 to 3 ohms as the range for my indicator. Now I'm not much worried about my oscillator side of things, as it's fairly easy to come up with an oscillator. The one that really bothers me is the detector circuit. I really don't have the skills or the knowledge to build one of those, so I do what every good engineer does. Go out and look for a reference design. A Google search gives me about 4K plus results, so I think I have something to work with. After reviewing all the designs I found, I was able to group all the detector blocks into basically one of 3 designs. First is a resonant frequency type design, second a balanced circuit type design, and finally an amplifier design. So I've already gone over how knowing the resonant frequency of a capacitor will give you the ESR, so we know how that circuit works. The balanced circuit works by using 2 voltages of the same value, with one running through the device under test. The difference between these 2 paths are used to measure the ESR. Now in the amplifier circuit, the circuit is first zeroed with the circuit signal. The signal is then passed through the device under test, and any resultant change is greatly amplified and appears as a deflection from zero at the indicator stage. So I decided to go with the amplifier circuit for my detector block. And for the reference design, I pulled the one from our good YouTube friend, Whiskey 2 Alpha Echo Whiskey, Alan Woke. This design uses a single NPN transistor for the amplification. The amplified signal is then sent to a DC restore circuit, which is 1/2 of a dual op amp that's set up as an active positive clamper. This keeps any amplified signal above 0 volts. The signal then travels into the other half of the op amp that is set up as a buffer. As we are dealing with very small changes in voltages and hence currents, a buffer like this is almost mandatory. It both follows our applied signal exactly And any power we will use to run our indicator block will not weigh down the circuit, as it will come from the power rails of the op-amp and not the signal itself. Now for the indicator block, I was hoping to use the good old LM3914, as a few of the meters I've seen use it, and you can get a nice indication using red, green, and yellow LEDs. I also have a large pile of analog meters. I'm pretty sure I can make one work. The point here is that I'm not going to give an absolute value of ESR. I'm just really going to give an indication of whether the cap has low, medium, or high ESR. So with all that being said and done, let's go down and see what I put together on the bench.
Okay, so here's our circuit diagram from good old buddy A. Woke. Now, I did go through my inventory stuff and found out that I actually did have a 4049 for the oscillator on this one. Mine's about from 1970s vintage, so we'll see how good that was. I also, of course, had all the capacitors and resistors and diodes, and of course, who doesn't have a 2N222 lying around? I got a whack of those. The only problem I had was I did not have an 8032, so I had to make do when I was doing that with other op amps I had handy. I didn't really particularly want to go out and buy one like that. It was actually hard to find. And of course, I had a different whack of differing meters and stuff to go over, and I was also thinking of using this, but unfortunately, we can talk about that later. This one didn't work because I needed a whole other series of amplifiers to amplify it up to this level, so forget about that one. The old LM3119 or whatever it's called. So, now, of course, I had all the circuit diagrams. I also took, like good old Bob P's, piles and piles and piles and piles and pages and piles and pages of notes. So I had mostly everything documented by what I was doing and different notes on what to build things up. So, lots to go on. So, let's go have a look at what the circuit looks like. Let me just move it over here. There we go. So, the overall of the circuit isn't particularly extensive. I did all my oscillator testings on this side of the breadboard. Then I did my amplifier right here. Of course, the amplifier is very much. And then my DC converter and buffer here. And of course, then it's the output resistor arrangement for my meter. And there's my meter on the other side. I eventually happened to find one that was a microamperage that worked really well. So, shall we give this a quick power up? Okay, let's give this a real test now. This is the output from my oscillator, and I'll put that at the beginning of the test to short it out like we're supposed to, and I'll throw the power on. And the meter should come right up to about 5. It bounces around a bit and moves around a bit because there's a great deal of parasitic inductance and extra resistance from all the wires. Hopefully once I get it put on a PCB, most of that will disappear. Anyway, that's good enough 0. I'll bring in a 5 ohm resistor and hook that up, and you should see the full scale. There it is. A little deflection down there. I'm not too sure if you can see it, but it does move. So that's full scale. Okay, we can take that, turn that off, and take that away, and we can do a little bit of explaining what I did in the circuit. The first part of the circuit I built was the amplifier and DC restore and the buffer. Of course, I didn't have any trouble getting the 2N222. Set that up fairly quickly. The real problem was the op amp. I started out with a TL072, as that was a railed single supply one I had, and one of the only amp amps I had. Unfortunately, that was just too slow. It wouldn't work with the amp meters I had. It was either putting out a very small range or way too much power for any of the amp meters I had. So then I went for a LM6482, and that was a dual power supply. The only problem with that, it was too fast. I was getting a micro small change. You know, for a full 1 ohm, full 10 ohms, I wasn't even getting a deflection back to 40 on this particular microamp meter. So I need to get a much smaller amp meter to test things. Finally, I found a 6442 to try in there. The only problem was I had to use the dual power supply, and since I don't have a dual power supply, I had to use a stupid battery pack at 4 volts or so, and then reduce my voltage to 4 volts. Really have to build a op-amp power supply to work with these things. So after that, I went on, I got it working. It gave me basically a full scale of 3 ohms, 2 ohms. It was actually working. And I was actually not using an oscillator. I was using my signal generator out of the oscilloscope set at 5 volts. It was actually working fairly well with that. So then I went on to start building the oscillator. So saving the easiest part for last, I built up here the 4049 I had, and of course the only problem I had with that was that I really didn't get a particularly fast square wave. I think I was getting about 5 kilohertz at 5 volts. It's a good square wave, but just not very fast. Not the speed I wanted. So then I went on to try out numerous different op-amp configurations. The really only funny ones, I was trying an LM358. Problem was with that was I kept on getting a good square wave up until about 20 kilohertz, but once I started pushing it, I would begin to get a triangle wave, and then eventually a sine wave, and then just garbage. And that was because I was running out of slew rate for that op-amp. So then you tried up all sorts of stuff, and so then I tried the 47121, and I discovered exactly what a monostable pulse generator was. I spent maybe 2 or 3 nights playing with this thing trying to get it to oscillate, and then I discovered after reading numerous places all it does is put out a pulse of a set length. So really not what I want. It is a at least I know what monostable generator is. It means it produces one output for a stable amount of time. So eventually I fell back to my one of my surface mounts op-amps. Worked really nice, but then again it was a dual. I got it right up to 400 kilohertz, no problem with the square wave. The only problem was, like the 6442, it was a dual power supply, which I wanted to stay away from. So then I fell back to the good old triple nickel. Now the triple nickel, this is an old one from the probably the mid-80s I had lying around. It did not produce a particularly good, I could produce a sine wave of about 100 megahertz, 100 kilohertz, but it just was not of any good quality. It would start to oscillate, it wasn't very stable, I would get spikes all over the place, despite not because of the parasitic problems here, just because it just wasn't really designed to run that fast. Well, the bandwidth I needed. Fortunately, I had this guy here, which is a Texas Instruments surface mount. And that turned out to be fortuitous, because with this little 56K 1% mica cap, I was able to get a really nice 100 kilohertz square wave to generate out. And that's the one you see working with that. So using an SMD surface mount device for the oscillator turned out to be a good thing in the long run, because I had to use one here anyway, so that means I'd have basically an SMD project. I don't mind, I like working in surface mount. Really now I had all the parts I needed to create it in surface mount. The only thing I didn't have was this little 56 picofarad mica cap, but I just left that in. You can have one surface mount part, one through-hole part in the surface mount device, I don't mind about that. The only other problem was I didn't have a 2N222 surface mount. So I had to find another transistor I had in surface mount. I happen to have a 2N5551 in surface mount, and I happen to have one in through-hole. So I added that in. I had to rebalance the entire circuit. So after I did that, rebalancing it took me a long time to get it to work again, because this amplifies a lot more than the 2N222. Eventually what I had to do was I had to put a pot on one side of the, if you look at the circuit diagram, I had to put a pot on here for the biasing, and I had to put a pot on here for the bleed out on the op-amp DC restore. So I used 20 turn pots and managed to hook them up nice, and eventually, rather than a 3 ohm scale with the 2N222, I got a 5 5 ohm scale as you saw before. So next we'll run through some capacitors which I've hooked up to see if this thing actually works. Okay, so one of the nice things I have lying around my bench, I picked up a long time ago one of these, is one of these. It's a standard 1 ohm. God knows how old this thing is. Must be well up into the 60s or 70 years old. Could even be World War II vintage. But the great thing is I can calibrate my meter really well. So we'll throw her on here, put it at 0 ohms. There we go. Let it warm up a bit. Like I said, it's not particularly, it's pretty feeble. Okay, there it's at. And let's put in the 1 ohm. Put that there. Put this here. Get it out of there. Hook it up. And we get 1 ohm at about 40. Right? Which tells me gives me a nice level. I'll be able to adjust that later with these pots, but I'm not going to do it right now. So we know 1 ohm is about 40. Let's go get our test caps. A whole row of test caps, and we can go through them now. Put this lead in there. So here is a really old stock, never used cap. And that's way down at the other end there. So we know that one's bad, or at least should be checked. Here's a more old stock one, but a higher quality one, and that's way over there. It's got less than 1 ohm. And this guy here is a new Nichicon. If I can get the right one. Right there. And that's a good one. Here's another Nichicon, another new old stock, but a good one. Again, 1 ohm. Here is a cheapy cap, Chinesium, a little over 1 ohm, but you know, it's fine for using it for some projects. And here's one you might recognize. I blew this one in one of the pictures. I'm not even getting a reading out of it, just a little deflection, so well over 5 ohms. Here's a super low ESR one, which I know is a good one, brand new. Here's a pull out of an old stereo. That's still good. And over here I got a couple other older ones. I think this is a new old stock from about 15 or 20 years ago. Oop, just gotta put that in there, and I gotta move hook that up there. About 1. And here's another pull. If I know this one came out of a bad, this one came out of a bad switch mode power supply, and there it is, somewhere in the middle, so 2.5, 3 ohms. So there you have it. It all works nicely. It'll probably work a lot better once I get it on a PCB, and that'll be the next project, I guess. Next video, I guess.
So stay tuned for the next part of this project, where I create a schematic for my breadboard, lay out and create a PCB from the schematic, then try to pick out some sort of enclosure to put this meter into, put it all together, and hopefully I don't have to go back and do any rework.
Well, Riley, I can see you're really, really enthusiastic for part 2. Yeah, well, you just like your valves. You don't like transistors much, do you? But we can use this to make valves. See you later, Riley. Maybe you'll come down and help me later? I guess not.